In the previous video, we have learned about how to compute the SVD form. We talked about reduced and truncated SVD form. So in this video clip, let's talk about some applications of SVD in low-rank approximation and principal component analysis, or PCA. So the first one, the first application, suppose that A has non-zero R singular values. So they have R items here, and the last one is must be is positive. We know from the truncated form of SVD that you're gonna take only the portions of portion of U, portion of sigma, and portion of V. Um, just take the first R columns in U, take the leading RR subblock, leading block in sigma, and take the first column in V, first R column in V, and then transpose. So when you expand that out, it's going to be the sum of rank 1 matrices is going to be in the sum of rank 1, because you know that when you have an outer product of two vectors, U and V transpose, this is always rank 1. Okay. So in order to reconstruct A, you need R sum of rank 1 matrices. So in application, suppose you have original matrix, but you don't want to store the information, for all the R sum. So you can take only the sum up to some number that is less than R. So the approximation of A can be lower rank than R. So in this application, it would be interesting if we explain by imaging analysis. So suppose you have an image. Usually an image, the color image, it can be stored in RGB format, right? So which means that if you read a matrix if you read an image into the computer, that will be three layers of matrices, three matrices according to RGB channel. And each matrix, it contains the pixel intensity in the value of 0 to 255, all right? So your matrix is going to be in the format of width and height, width by height, and the resolution is in terms of pixel. So if I what we can do is that for each matrices, we take the SVD, we take with SVD of R channel, we take SVD of G channel and the B channel, right? And then what we do is that we take only the sum up to R term, where R is 1. It means that you only take the rank 1 of R channel, B channel, and G channel, and then you sum up into the image, and that is what you're gonna get. So you see that only use the first term, the sum of rank 1. The final image is going to be very blurry, and that is going to be just a very rough approximation of the original one. And as you see, as you increase R, if you use 10 terms in the sum, so you collect more information. You use the R sum, so it means that you use sigma 1 to sigma 10 into the sum. And as you keep increasing R, here it's 80 terms. So it looks like 80 term is enough to get the same information of your image as the original one. Okay. So this is an approximation. Um, because the original one, if you read, so maybe the sigma, the sum that you would take would be in the order of 1,000, whatever that value that according to to the size or according to the number of original non-zero singular value in the matrix. But here in this result, it means that you can restore the image up to 80 terms, and you keep about the same information, the same amount of information in the picture. About the low rank approximation, we have a very interesting theorem, Eckart-Young theorem. It says that if you have a matrix A of rank R, okay, and X of rank K, where so X has any X that has rank K, and K is less than R. So basically, X has lower rank than A. Okay. So if you are interested in a question like I have original matrix A that rank is full or some rank, but you want to approximate A with X, but X has lower rank than A. So if you take into the class of all the matrices that rank of X is equal to K, so which one is closest to the original A? The answer from this theorem says that the matrix that use the singular value decomposition up to K term will be the solution. Okay, so so rank so the norm here is the two norm, rank of A minus AK, where AK is the the singular value decomposition using the K term. The norm of this will be less than norm of the other X that has rank K. Okay, so this is the result. I think we can illustrate this as well. For example, um, so let's think about some easy example when A is diagonal. You know, when A is diagonal, the singular value and the diagonal entry will be the same. Okay. So here A has the original A has rank 4. Okay. So what if I'm talking about the problem of I wanna estimate A with X, where rank of X must be 2. So I'm looking for rank 2 approximation. So in the previous Eckart-Young theorem, it says that if you use A2, that is the sum of sigma k, uk, vk transpose up to 2 terms. So that's going to be, because the diagonal case is simple, that's going to be 8, 10, and 8, right? Okay, so Eckart-Young theorem claimed that this is going to give you the best approximation. So what I'm going to do is that let's think about some other heuristic solution. Let's think of other candidate to compare. How about, so I'm going to use the letter B instead, B2. Let's think of something that has rank 2. What about we make a sum of 10 and 8 and then take the average? How about this one? So this guy has rank 2. This guy also has rank 2. Okay, and then we're gonna see the error in MATLAB. What about C2? C2 is another rank 2 matrix. How about we construct 999 into subblock? All right, because you know that this portion will have only rank 1, right? So I'm going so if I construct in this way, this gonna have rank 1, this part has rank 1, so the total here is rank 2, still rank 2. Or I can think of the 2 that is 99 here, 999, which seems to be just heuristic, just the average of 10 and 8. And what about D2? We take the average of 5 and 1, which is going to be 3. Okay, and then we create this one. So all of these candidates has rank 2. Okay, so obviously with this choice, a minus a2 is going to be 0 0 0, and then 5 and 1, right? A minus b2 is going to be 1 and minus 1, and then minus 5, and then minus 1. All right. So we can, because the diagonal case is simple, we know that the norm of a minus a2 is going to be 5. This choice, the norm of a minus b2 is also the eigen of the eigen of this transpose this, right? So this is going to be 5 as well. But for this one, I'm going to calculate in MATLAB. So what I just explained, so I create the code in this code of MATLAB, right? So this is my original A. This is the one that I claim to be optimal, the one that construct from SVD up to sum of the two terms, all right? So B2 is the heuristic one, just 9, 9, the average of 8 and 10, all right? And C2 is going to be subblock, and also subblock. And for D2, I construct this way heuristically. So my D2 is going to be a tall matrix, all right, tall matrix, and then I construct the outer product. So D2 will have rank 2 as well. So now if I run this, you're gonna see that see the results that I compare all the norms, right? Compare all the norm, and you see that the original one, this is the norm of a minus a2, the one that I claim to be smallest, right? The other one is equal to the one that I claim to be optimal, but the other ones, the other two, give me the higher error. Okay, so this is to illustrate that in this example, if you construct the SV construct the best low rank approximation is going to be from SVD decomposition, but you use only the term up to your number of the rank you want to use. Okay. In other I'm gonna do another example as well. Let's say um in another example, so I'm gonna generate I'm gonna generate a n by n, all right? And my question is that what is the base one rank 1 approximation? What is uh the base x that x has rank 1, but it's going to be the base approximation of a? Okay, so by principle, of course, the Eckart-Young theorem says that if A is U sigma V transpose, the best rank 1 approximation is going to be A1 that use only sigma 1, U1, and V1 transpose, only the first term, right? And for any other matrices that has rank 1, the norm of the difference will be higher. So I'm going to generate B1, which is another rank 1 matrices. I'm just going to use it as like X and Y transpose, the outer product of some random X and random Y. And then I'm going to compare. I'm going to compare A minus A1 and A minus B1. Okay, let's see from the code. So here's the code at the end. Okay, so let's see. So I generate, let's remove the screen. I generate A that is randomly 3 by 3 from normal distribution, and I perform SVD. So my base rank 1 approximation is going to be sigma 1, U1, and V1 transpose. All right. And next, what I'm going to do is that I'm going to generate B1 that is going to be some outer product of some random vector. So this is like X and Y transpose random. So this is guaranteed that my B1 has rank 1. And I'm just going to compare norm of A minus A1 and norm of A minus B1. So you see that norm of A minus B1 is always bigger than the base rank 1 approximation. So why don't we generate it again and see that for any other rank 1, B1 is going to give bigger error than the best solution. Okay, so this is to illustrate the first application of SVD. And the next application is principal component analysis or PCA. In machine learning, we work with feature that may have a higher dimension, maybe in the order of 100 or 1,000, all right? And usually you have data matrix, okay? Your data matrix, if it's in the format of P by N, it means that it has P features and it has big N samples, okay? And in this picture, it suggests that originally you have data in two features, two dimension, but then it seems that when you make a scatter plot in this way, it seems that the data is very correlated, and when you see kind of the region of data, it means that if you somehow you rotate or change the coordinate the data into this direction, okay, these directions seem to have the most diverse data along this dimension. It seems that along this dimension the data has highest variance. So in the context of learning the model from the data, in that sense, you want your data to be informative, and in that sense it means that you want the data to have higher variance. So you don't prefer the data that seem to be cluster or concentrated at some value all the time, right? And for those data, these data has small variance. Okay, the data that should be useful or amenable for your model to pick up the dynamic, the pattern of the data is the data that has fluctuation, that has higher variance in that sense, right? So in this question, in the question of PCA, it seems that data in this direction has higher variance, but along this direction, it has very low variance. So if we can reduce the dimension to one dimension only, probably we should pick the data or transform the data along this direction. And this is a question of PCA. If you can reduce the variable dimension by transforming the coordinate, all right, and select only a few of the features, what will be the direction you pick? Okay. So first, we can answer that by first taking a look at the data matrix that in the format of RP by N. In that sense, which means that you stacked your P features along each row, all right? If you arrange the data matrix in this way, the covariant matrix is going to be X transpose divided by N minus 1. Okay. So everyone knows that for the covariant matrix, all right? So in this case, it's going to be P by P along diagonal of covariant matrix is going to be the variance of each feature. All right. So if I'm talking about total variance in the data, I should probably take the trace of C. So I take the trace of C, so the trace of this, and because of the circular property of the trace, trace ABC is going to be trace of CAB, is going to be the trace of BCA. This is called circular property. So trace of X transpose is going to be trace of X transpose X. So it's going to be the same as the Frobenius norm of X, right? So that's one thing. And that is the total variance. So let's take a look at the connection between the total variance and the singular value. It will be no surprise that when you see that, of course, when X is, if you perform SVD on the data matrix, all right? So C, which is X transpose divided by n minus 1, you substitute U sigma V transpose in this, and then you get this matrix. Okay, so you get this matrix. I hope it's not hard just to plug it in. But from there, from there you see the connection, because the trace of C, that's going to be the trace of U sigma square U transpose divided by n minus 1. And of course, because of the circular property again, is this, right? Is this. Where this becomes identity matrix. So that's why if we take a look at the covariance using the SVD form, we see that the total variance in the data is actually the sum of, because sigma square is going to be the singular value in the diagonal, right? In the diagonal. So um, here we take the sum. So that's going to be the sum of sigma 1 dot sigma r square. And do not get confused. This sigma is the singular value in sigma, and sigma is the a singular value of X of the data matrix. Do not get confused between the sigma that we might use for variance, but in this context, this sigma notation is for singular value. Okay. So total variance can be expressed, so finally, total variance can be expressed as the sum of singular values, of the non-zero singular values. What if we wanna use only a few features? All right. Remember that we wanna pick. We originally we use p features, so we wanna transform x into some variable y, and y is gonna be something that is less than p, less p features than p. Let's say what did I use in the slide? Maybe k, right? K by n, but this k is going to be much less than p, for example. At the same time, when we want to reduce the dimension, we also want to keep a portion of the total variance to be not much less than the original one. So we know that the total one is this. So how about we truncate only k of them? Okay. Suppose it's going to be like this, all right? So suppose this is suppose this is the cumulative sum of your singular value, all right? So the first one is this. So if you truncate, sorry, if you take the cumulative sum, all right? Cumulative sum. So it's going to be increasing, sorry. It's going to be increasing, all right? You know that if you want to take it all, if you want to obtain the total variance, you must use all the singular value. But probably you don't have to use them all. Probably from this graph, you can see that maybe if I use around this one, maybe, for example, maybe around 4 or 5, all right? You get the same, almost like 80%, let's say. You get almost 80% of the total variance. So why don't we reduce to use only the first 5 features? Okay, so this is a place where you can perform the SVD. Okay, So in PCA, what you do is that you're going to perform SVD on the data matrix, right? So now it's use R term, all right, totally. So you're gonna pick the first K principal loadings, all right? So this is U1.uk. And what is the number K here? The number K is account for the fraction of the variance that you think that is gonna be the quantity that you want that is quite just drop a little from the total variant. So this is going to be up to your choice, the number K. And now you're going to use that u1.uk, okay, um, to transform, you stack u1 UK in this way, and then you transform uh, uh, u on x in this way to get the new variable y, okay. And Uh, yeah. And then let's see some examples. So in the new dimension, in the new dimension, these will be sorry, these in the new dimension of y, this will be k by n. That is, and k is gonna be typically is gonna be less than p, and this is up to the user choice. Okay. For example, for example, in this one, in this one. X has two features, and this is 1, 2, 3, 4, 5, 6. They have 6 samples and 2 features, okay? And they have totally 2 singular values, 16 and 3.9, okay? So in this simple example, let's say that I can keep only the first loading because my sigma 1 is much less, is much higher than the sigma 2. So if I decided to use only one dimension instead of two, I use only the first loading. So I take the SVD of X, so I get U1, right? And I transform U1 transpose X. So it's going to be U1 transpose X, and this is the SVD combination of X. And the result is going to be that because you want transpose, that's orthonormal, right? So this is norm of u1, which is 1. So that's why you get sigma 1 v1. And for this term, it's going to be orthogonal. So this term multiply this term will be 0. And this seems to be the new data matrix that is less dimension now that you're going to use for further analysis. Okay. So that's the two application that I would like to illustrate the benefit of having the SVD factorization.